Hi, I'm Martin Plenio. I'm a professor of theoretical physics at the Center of Quantum Biosciences at Ulm University. I was actually a third-year undergraduate student at Göttingen University, which is quite close to the border to the East Germany. And in the evening I was out and about and I started to see all these trabbeys driving around, and that was a sure sign that something must have happened. And indeed, the wall came down. And for this research project, that had a real impact, because in the end it meant that myself from West Germany and my colleague Fyodor Zheletsko from Belarus originally could come together to conduct this research. When I was little, I actually wanted to be a pilot, ideally the captain of a 747.
Did this wish come true?
This did not come true. And the closest I came to this dream was one day at Heathrow Airport when I actually entered the cockpit of a 747 that I was flying with and started to chat with the pilot. And I was very much in awe of everything until it turned out that the pilot actually was a fan of popular science books about quantum physics, and I told him about our work. And so in the end, we were both a little envious of each other's job. So, you all know MRI machines because in the clinic they help us to look into your body without cutting you up or without using harmful X-ray radiation. So how does it work? Well, what an MRI machine really measures is the magnetic field that the hydrogen atoms in your body are creating. So where's the problem? Well, the problem is that these hydrogen atoms, the magnetic moments, are randomly oriented and therefore mainly cancel each other out. And you can see this very nicely here. I have two magnets, anti-parallel in orientation, and when I hold them close to a magnetic needle, you see that hardly anything is moving. So what we have to do is we have to make these magnetic moments, we have to orient these hydrogen atoms parallel, because then we see at the same distance we get a much stronger reaction because the magnetic field is stronger. That would allow us to get a bigger signal and resolve much smaller structures. So we understand that the key problem is to align the magnetic moments of the hydrogen atoms to get a large MRI signal. Now traditionally this would be done by taking a sample, placing it in kind of a really big fridge, which is run on liquid helium, and then we would just, wait until the sample is really cold and the magnetic moments have aligned. Now we take a really fundamentally different approach by avoiding this waiting for thermal equilibrium and staying out of equilibrium actually. And we do this by a process that we call optical pumping. And that uses very short laser pulses that force the hydrogen atoms and their magnetic moments to align. And in that manner, the process becomes much more efficient. With our research, it will now become possible for the first time to image in an MRI machine small quantities of molecules that are really essential for the metabolism in tissue. And this has a lot of potential applications. So for example, it might become possible to decide within hours whether a tumor reacts to a treatment. Or after a heart attack, we may be able to actually very efficiently assess the state of the heart muscle. And so in order to realize these kind of applications, it's our dream that with every MRI machine in the clinic, there will be one of our devices side by side to it. So in our research, we have really identified and demonstrated all the basic ingredients that we need for our technology. But the big challenge that still remains to be answered is that we have to take this technology now and turn it into a device that we can put in the clinic where it works at the press of a button.